So let's look at touch. We're gonna look at touch first, and then we'll look at all of our special senses. And that's where the fun stuff is. All right. So when it comes to our cutaneous receptors, we have free nerve endings. We have Merkel's disc. I didn't put free nerve endings. Oh, there they are. Okay. Free nerve endings, Merkel disc, Meissner's corpuscles, Ruffini corpuscles, and Pacinian corpuscles. Okay. So from kind of top down, that's kind of where you generally find them. Free nerve endings are up closer to the surface. Merkel's disc are found closer to the surface. Meissner's are found closer to the surface. And then Ruffini is kind of in the middle of the dermis. And Pacinian is very kind of towards the bottom of the dermis. So all of these are involved with touch and pressure. And some of them will have special structures around them. Well, all of those guys will have special structures around them. And by special structures, I just mean, like up here, free nerve endings. It's just, here's my nerve, and it goes into the skin. That's it. There's your dendrite. Okay. These are carrying a whole bunch of stuff: pain, cold, heat, some touch, even though that's, it's not necessarily, what we think about, but it'll carry anything. It's not specific at all. Okay, these free nerve endings: pain, cold, heat, touch, light touch, not very specific at all. When you look at these, that dendrite will have some special adaptations around it. Okay. Okay. We'll have a bunch of special adaptations around it. And let's just, I suck at drawing, so let's just go over here. Okay. Where am I at? There we go. Okay. And here you can see free nerve endings is the free nerve ending. Nothing really spectacular. But here you can see Merkel disc. It looks like a fan. They don't show it very well. When you look at it, here's kind of the ending of it. It looks like a fan. Kind of like that. That's Merkel disc. But you can see these are, they have a wrapping around them that gives it some degree of specificity here, where you can interpret lighter and deeper types of sensation because of these fancy pants wrappings that you find around them. Free nerve ending, as soon as somebody touches your skin, boom, it's firing. Okay. And again, it carries a multitude of different things, and it's not very specific. Right? But we have a ton of other specificity. Here you can see Merkel's disc up in that epidermis, Meissner's just in the top portion of the, excuse me, top portion of that, what am I trying to say, dermis. Ruffini kind of scattered around the midsection here. Pacinian, you can see they're deep, but you can have them up here as well because, there's degrees of extensions there in terms of deep touch. All right. But all of these will have special structures around their dendrites, which gives them degrees of specificity. Right? To that end, I have something highlighted, I believe, on yours. If it's not, those are the things. That's the specific sensation that I would like you to know for those things. Okay. Free nerve endings are kind of a catch-all. They do everything: light touch, hot, cold, pain, anything and everything. Okay. Again, not very specific. Right? They can be found scattered in the skin itself. You can find them wrapped around a hair follicle. They're all over the place. Okay. As you can kind of see, unmyelinated dendrites. So, myelinated is what you see with these guys here. These guys have some kind of myelination around it, some kind of capsule around the dendrite. So again, that gives us some specificity. Merkel's disc is more sustained touch. So as soon as something starts touching your skin, these Merkel discs are going to trigger off. You usually find them in the stratum basale. So light sustained touch is going to be their bag. Ruffini looks weird. And if you think of it like a Chinese finger trap, Chinese finger traps don't really work until you start to stretch, try to pull apart your fingers. To me, that's always how I thought Ruffini looked like. So it's involved with stretch. So maybe that'll help you. The other two are kind of interesting. Meissner's corpuscles and Pacinian corpuscles. Pacinian is always involved with some kind of deep touch, deep pressure. All right. For me, I think of the Pacific Ocean. The Pacific Ocean is deep. So for me, I always associated Pacinian corpuscles with deep touch, deep pressure. As you can kind of see, fast vibrations. Don't worry about that. Meissner's corpuscles is much more softer touch. And softer touch, with a soft touch, you can determine change in textures. Okay. If you sit there and paw at something, you wouldn't necessarily be able to feel all the subtle nuances of something, the textures. But when you touch something really light, you can figure out all those various different textures that you're touching. A Meissner is somebody who's old and crotchety, and it doesn't take much to set them off. So for me, I always associated Meissners with light touch / texture. You can kind of see where they're located here. I'm not necessarily going to ask that. Okay. But what these things pick up, that would be something that, again, probably would make a good matching question or multiple choice type question. But these are all of my cutaneous receptors right here. Okay. Again, they're all mechano in nature, right? Free nerve endings are mechanoreceptors. They're nociceptors. They're thermoreceptors. So not very specific, but Merkel, Ruffini, Meissner's, and Pacinian, they're all mechanoreceptors. They're touch. Sorry. These generally trigger, sodium ion channels or calcium ion channels. So usually when something cold touches your skin, those thermoreceptors are going to respond to it by opening up sodium channels or calcium ion channels. And that's what's going to cause the excitation for these. Okay. I didn't write it on there, but there it is for you. Okay. You have a lot more thermoreceptors for cold than you do heat. Okay. Stimulated by cold, inhibited by warm. And it'll be opposite for warm receptors, obviously. They're stimulated by warmth and inhibited by cold. When you hold an ice cube in your hand, let's say, it is those cold receptors that are going to be triggering themselves and they're going to depolarize. The warm receptors are going to be hyperpolarized, right? So they're not going to be sending in any information. So then you interpret that thing as, oh my gosh, that's really cold. As you can see there, methanol is similar to these as well. It's the same receptors that get triggered, these cold receptors. So when something with a lot of methanol touches your skin, you interpret that as really cold. I may ask a temperature range because it is specific. Right? Because it is specific. There is generally the cold receptors, the temperature range for response. So again, on the lower end of that spectrum is going to be cold, and on the higher end of that spectrum is going to be hot, the hot receptors. Anything above, I can't remember, I think it's on the next slide. Anything above like 110 or something like that is going to stimulate the hot receptors. Okay. Yeah, 109. 109. This is also going to trigger some pain receptors as well. So you also get some of the nociceptor activation with this one as well. And there is a gene for capsaicin. There's a gene for interpreting, spicy hot foods. Some people have an overactive ability to react to capsaicin, so they interpret that as a hell of a lot more hot. So there are some genetic kind of markers in this world when it comes to how we perceive stuff that's hot. I am not a hot, spicy person. I don't like it. And I have a couple genes that cause my capsaicin receptors basically to be exceptionally sensitive. I know, I'm a sensitive man. But it's interesting because my dad loved hot stuff. I hate hot stuff. God, I hate hot stuff. My son, he loves it. He puts hot sauce on everything. I just look at him in disgust because I don't understand how that happens. Because for me, good Lord, I'll be down for like a week. Warm receptors are located deeper in the dermis. Again, excited by warming, inhibited by cooling, and that's going to be, there's your range right there. Okay. When you start to get a little above, there's going to be some degrees of, is this painful or not? And again, that's going to be on the individual with how sensitive some of those hot receptors are. All right. But here you can see the more and more on the higher end of the spectrum, the more of those warm receptors getting into hot receptors. Okay. On the lower end of that spectrum, obviously all cold receptors going to be involved there. As you can kind of see, anything below 46 is cold. So if you get cold enough, has anybody sat their ankle in a bucket of ice water? No? Anybody ever roll your ankle here? Have you guys lived? Oh my God.
Yes.
Yes, there. Thank God. Okay. You put your foot in that bucket of ice water, right? Because you've rolled your ankle again. And you're like, oh, okay, this is not too bad. And then all of a sudden you're like, holy gosh, this is really cold. And then, oh my God, it feels like somebody's stabbing you to death because it triggers all these pain receptors, okay? Because as you get lower and lower and lower towards freezing, that's going to start to trigger some pain receptors. And you start to interpret that as a burning sensation, okay? And then finally, we just numb it out. And then you don't send anything in there anymore. And that's when you start interpreting that numbness. You've basically, frozen that nerve receptor, which is fantastic. Until you get to that point, it stinks. So the question on the chat is, would that be the same for frostbite? Yes and no. We will talk about, and I can't remember if it's in the cardiovascular unit, we are going to talk about blood perfusion into a couple different, like the brain, skeletal muscles, and the skin. And we will see what happens because it's a sympathetic event and parasympathetic event going on there within the receptors into this region there. And that's going to affect blood flow into that region. And that can help with deadening the sensation in that region. So with frostbite, you have a massive kind of sympathetic response, and you have decreased blood flow into the skin. And you also have obviously very decreased blood flow from the skin. And so you have a buildup of metabolic waste products, which is going to change pH, which is actually going to cause some pain. Okay. You're not going to be able to remove that waste product from the region there. So it's going to accumulate, and that's going to, oh my gosh, my hands aren't going to work very well. Then we have decreased sympathetic flow into the region as well, and that's going to deaden some of the receptors as well and whatnot. So when it comes to that, it's multifaceted, okay? Multifaceted, but that's a great question. Okay, and we'll talk about that in cardiovascular unit. Two units from now? Yeah, 2 units from now, I think. I don't know, I can't remember. But pretty simple. All right. here is pain. Pain is fascinating. We have basically fast pain and slow pain. Fast pain is fast. I'm just going to put P for pain. Fast pain is A delta, yeah. A delta fibers. Slow pain, slow P, C fibers, yeah. Just for grins and giggles. How fast is this one? 28. Those are just some conduction speeds, just to kind of give you kind of a concept of what is really fast and what is really slow. And there you go. Excuse me. You can see kind of slow pain is very dull. It's just persistent. It's just always there. It's unmyelinated. So this is going down the entire length of the axon. And obviously it's going to take a whole heck of a lot of time. These are also small. These are small as well. These are also some small as well, but they are myelinated. So you can see that myelin does really affect and change how fast action potentials can travel down an axon here. So with our fast pain, it's more sharp, very sudden, jabbing you with, a pen, jabbing you with a needle, okay, very quick. When it's much more duller in nature, we're triggering more of the unmyelinated neurons being stimulated. And again, you can see kind of the difference and change there with speeds. I'm not going to ask the speed, just fast or slow. Just keep it general. I just put it there to kind of give a visual. When it comes to pain receptors, they are triggered by a multitude of things. It can be some significant mechanical stimuli, rug burn, somebody's grabbing your skin and just kind of yanking and pulling and twisting in all different directions there. That's pretty extreme mechanical stimuli. Change of pH, damage to tissues. There are a number of different chemicals that get released when you damage a blood vessel, let's say, or if you damage tissue. There are a number of different chemicals that the body tissue will release, and that's going to trigger some pain receptors within the region as well. So they can be activated by a multitude of things: extreme temperature, extreme cold, hot, extreme heat. Okay. So when it comes to pain receptors, it's not very specific because it's all carried in those free nerve endings, right? That's why you can put your hand under scalding hot water and be like, oh my gosh, that's cold, but it's like hot. Again, it's carried up in the same labeled line to the brain. And we just interpret it really fast. Okay? Where, you put your foot in a bucket of ice water and you're like, all of a sudden it's like burning, like it's hot. And obviously you're in a bucket of ice water, so that's not the case. Not specific. Not specific, so our brain can interpret that a multitude of different ways. Extreme cold, extreme hot, painful. You can suppress pain. You can do it. There's some people who can, meditate and get rid of it. And there's actually there's a whole science on it. It's kind of interesting, but that's more of kind of psychological in the brain. And I don't want to get into that. But you can get rid of pain through mechanical stimulation. You're like, holy crap, hold on. You just said mechanical stimuli can cause pain. Yes, it can. But mechanical stimuli can also inhibit that pain as well. It's referred to as the gate control theory of pain. Okay. we have a number of pain receptors that, again, are C fibers there. Okay. Comes in here, synapses on a second order neuron, usually within the central nervous system, within the spinal cord, and it goes up into the brain. Okay. And we'll interpret that as, whatever the pain sensation is. Okay. But you can see here, here's an inhibitory neuron. Here I see this slow fiber here coming on up and stimulating. And that helps us to send that pain stimulus up to the brain. You can see here it gives off a collateral branch. And this is inhibitory. And it stimulates, or it doesn't stimulate, this inhibitory interneuron. It hyperpolarizes it. Okay. So this thing is not stimulated. We have a number of fibers, mechanoreceptors. As you can see, this is some fast pain. Alpha beta fibers, kind of small to myelinated, where they can give off a collateral branch and stimulate that inhibitory neuron. So this is going to cause this thing to not fire as much, okay? Because it's a negative effect on this dude. And I think I talked about this last week when giving some examples and talking about some fun stuff. When you sit there and you nailing that thing into the wall, trying to hang up that picture of you and your girlfriend or boyfriend, and you whack your finger with that hammer, you start to move it around. You rub it, okay? What do you tell a kid whenever they fall down? Rub it. Why the hell are you telling them to do that? Because it will stimulate some inhibitory neurons. Okay. If I stimulate this inhibitory interneuron here, it inhibits, it hyperpolarizes this thing. So now it does not fire as much. And I don't feel the pain as much until ultimately I've done stimulated this pain receptor here and it's not firing at all. Okay. This is the gate control theory of pain. They've done a ton of research into it as of late, so it's kind of an interesting concept, even though it makes total sense in how it works. Okay. Anything can stimulate these alpha beta fibers. Okay. Touch. Oops. Why that does that? Touch. Vibration. Okay. Pressure. Why do you put an ACE bandage around people who have pain? This is that same concept here. Okay. So when you roll your ankle, yeah, you wrap it up, right, to help limit the swelling. Okay. That just helps to kind of push it out of the region though. But that constant pressure that ACE bandage does to the skin helps to stimulate this inhibitory interneuron. So why do you put an ACE bandage around people who've screwed themselves up? That's why. It helps to stimulate inhibitory interneurons to lessen the feeling or the perception, I guess, of pain. So that's how you do it, through mechanical stimulation. Sometimes I've asked it as a short answer question. Sometimes I've given real world situations where I talk about, rock climbing and falling or twisting an ankle while running, some of the receptors involved with that, how you perceive it. So sometimes I've asked a question like that as well in the exam. So there it is right there. I think I mentioned that earlier. Again, it's sodium and potassium, or sodium and calcium involving this excitation event. Okay. Isn't it always sodium and calcium with an excitation event so far? So we talked about with the graded potential, With excitatory postsynaptic potential, right? Sodium rushes in and it travels a short distance. What did we talk about with voltage gated channels for traveling an action potential down an axon? Sodium voltage gated channels open up, right? And that causes the excitation event. Calcium is an excitation thing. Calcium generally will come into a cell and it will cause a cascade of events. Can move things, can cause excitation, release more neurotransmitters into a synapse. So sodium and calcium are always going to be our stimulatory things in here. So whenever I stimulate a cutaneous receptor, a touch receptor, okay, I'm getting these two things to flow in. Here is my Pacinian corpuscle. There's a fabulous picture of it. There's the actual dendrite right there. Okay. And there's all this lamellation over that dendrite ending there. Again, that gives me a ton of variability here in how I can interpret deep touch or deep pressure. Right? As soon as I get deformation of that dendrite, okay, I open this mechanoreceptor. Mechanoreceptors respond to mechanical events. You touching your skin really deep, okay, that stimulates this mechanoreceptor to open up. And you get an influx of sodium and calcium. And that causes that receptor potential, that depolarization event. It's always going to be sodium and calcium involving depolarization. Okay? Is there exceptions to the rule? Of course. There's exceptions to every single rule. But sodium and calcium are generally always going to be, except for one major exception that we'll talk about, is always going to be involved with that depolarization event. The degree to which that deep touch, the degree to which these lamellated, these multi-layered capsules deform through mechanical touch depends on whether or not I stimulate that receptor potential, that generator potential. Okay. Obviously, if this just goes in just a little bit, obviously I'm not doing anything. Okay. But the deeper that touch, the more deformation occurs, and then I can deform that dendrite, opening up that mechanoreceptor. Take the finger off, and there it goes back to being closed again. Okay. And there it goes back to being closed again. Short answer question? No, probably not. At least specifically talking about a Pacinian corpuscle. But if I gave a real world situation, you would talk about Pacinian corpuscles. You would talk about, was I talking about deep touch, lighter touch, feeling something for texture? Do I say you were running and you tripped, do I give a real world situation? Then you would talk about this and all the other receptors involved with it. Because I'll give you I'll tell you everything that person's done, what they're doing. And you'll be able to easily tell me which specific cutaneous receptors are stimulated in that real world scenario. Okay, so I could ask it like that. And I've done that in the past.